Some of the most profound statements in our entire universe say nothing more than this: a given quantity can never change. Such a statement is known as a conservation law, and if you've ever done some physics, you've likely heard of them, like the law of conservation of energy, or momentum. But as the brilliant Emmy Noether proved in her famous theorem, these conservation laws are actually just a consequence of something far more fundamental: the symmetries of our universe. But what exactly do symmetries and conservation laws have in common? To answer this question, we first need to answer another one. Why does light bend when moving between mediums? And why do soap films form minimal surfaces? Well, light always takes the path of minimal time, and soap films always minimize their surface area for a given volume. But while it may seem like two very different things are being minimized, light, soap films, and everything else in our universe is actually minimizing the same thing. It's this abstract quantity called the action, which is the sum of the difference in the kinetic and potential energies across each point in time. Everything in our universe behaves in such a way so as to minimize its action, and this is what we call the principle of least action. But what does any of this have to do with Noether's theorem? Well, if Noether's theorem is a bridge connecting symmetries and conservation laws, then the principle of least action is what's holding it up. To see what I mean, let's imagine we're in some place that's symmetric under translations, like the void of space. Now, what exactly does this mean? Well, we could move up, down, left, right, and everything would still look exactly the same. We wouldn't even be able to tell that we'd moved. Therefore, we have a translational symmetry. Now, let's imagine we release some particle, and it takes this path. If it chooses this path, then this path must have the minimal action. But since space is symmetric, we can move the particle over here, or over here, and it would still take the same path. In other words, this path minimizes the action no matter where we are in space. And Noether said that because of this, the momentum along the path must be conserved. If it wasn't, then some force would have to be acting on the particle. But then when we translated the particle, we would either be moving closer to the force or further away from it. There would no longer be symmetry in space, and the particle would take a different path. But that's not what we see, so there can't be any net force acting on any of these particles, and their momentum has to remain the same. We can consider other symmetries too, like rotational symmetries and time translational symmetries. Using the same line of reasoning, we discover the laws of conservation of angular momentum and energy. But Noether's theorem doesn't stop there, because symmetries pervade all of physics, from general relativity, the world of the very big, to quantum mechanics, the world of the very small. In fact, the whole standard model is built on the various types of symmetries that elementary particles can have. Symmetries, it seems, are the one true constant in our universe, because they exist at every scale. And as Noether showed us, we can harness them to probe true meaning from the universe, right down to its very core.